Howdy, folks. Today's exciting topic, we're going to talk about the planets in space and their orbits and what laws we've come up with to figure out their orbits, what forces keep them doing what they do. And of course, the two big names on this, Johannes Kepler and Sir Isaac Newton. So we kind of put them together because they were, real big with figuring out the orbits of the planets and the forces involved. Okay, you'll notice they're not perfect circles, right? They are elliptical. That was a big thing with Kepler, he discovered. And of course, the force involved gravity. Well, that was a big thing with Newton. All right, so we're going to start out a little lighthearted as always, a little Family Guy skit on what force keeps things in orbit.
Oh, yeah? Well, I challenge you to prove to me that I'm fat.
Okay, hang on. See this?
Yeah?
You know what it is?
Sure. It's an apple.
Good, good, good. All right, watch this.
What the heck? What is this? What is this, some kind of gag?
No, that's orbit.
Huh?
You have your own gravitational pull.
Now back to the Three Stooges.
Oh.
Silliness. But yes, gravity, the force that keeps the planets orbiting the sun, right? Without that, they would just be wandering off in space. And of course, mass is the big factor of gravity. The other one, of course, being distance. But the more mass you have, the more gravitational pull you have. And that's what the dog was making fun of right there. Okay? So here we go. How do the planets revolve around the sun? Well, the path, that circular path, we call it an orbit. Okay? And here it is here, of course. You can see the planet orbiting the sun. And then there's this other black spot we'll talk about. It's a focal point of the ellipse. Ellipses have two focal points. The sun is the one we're mostly concerned with. All right, so Kepler had three laws. His first one, all right, first law of planetary motion, the idea that the planets have elliptical orbits. They're not perfectly circular. And the sun is at one of those focal points. And of course, that's the governing body, right? That's what controls the planet in its orbit. But that they were these oval shaped, not perfect circles. Okay? And you'll see those 2 points there. Once again, those are the focal points, but we're focusing on the sun. Okay. How do we describe Kepler's second law? Well, you tell me. Watch this animation here and see if you observe anything. All right, did you notice that? You notice it's getting a little bit slower here, but then it starts to speed up, and it goes the fastest right there. Okay? And of course, this is Kepler's second law, right? That a planet orbiting around the sun covers equal area in equal time, and it does so by changing its velocity in its orbit. Okay? So in other words, the amount of time it took the planet to go this long distance is the same as it took the planet to go this short distance. The reason being that it's closer to the sun here, so it's traveling faster, and it's farther from the sun here, traveling slower. So even though those look like different distances, and they are, it'll cover those in the same amount of time because the planet is changing its speed while in orbit. Okay? If this takes 26 days to go from A to B, then it's also going to take 26 days to go from C to D. The area on the insides is also equal if you worked it out mathematically, which is interesting. And the rule goes that a planet will sweep out equal area in equal time. So literally the amount of area inside this kind of triangle equals that one. Okay? And there it is. Make sure you get it in your notes. Planet travels slower, covers less distance at this point. And over there, the planet travels faster and covers a greater distance in the same amount of time. Okay. And this, of course, is just reiterating that. In this case, we're closer to the sun, so we're going to be going faster. Over there, we're farther from the sun, right? Here's the sun, here's the planet. So, of course, you're going to be going slower. As you go from B to D, your velocity will decrease. As you go from D back to B, it will, of course, increase. All right? That's all controlled by, you guessed it, the force of gravity. Very good. The closer two objects are together, the greater the gravitational force. Okay? In this case, when you are farthest away from the sun, you probably remember this word, there's perihelion and aphelion. Well, when you're farthest away, A for away, that's when you're going the slowest. And when you're closest to the sun, perihelion, you're going the fastest. Okay? It will also look bigger, right? When you're closer to something, right? As I get closer, I look bigger. Same thing here. As the Earth gets closer to the sun will appear bigger. That was one of our proofs of revolution we mentioned in the lesson the other day. All right? If you're farther from the sun, of course, it will look smaller. All right. It gives you a nice little animation there. Okay. The third law of motion right here. Bottom line, the inner planets will obviously get around the sun faster and take less time. And the outer planets will get around slower and take more time. That's what his third law basically stated. The further a planet is from the sun, it must have a larger orbit. Therefore, a longer period of revolution. And of course, closer, the exact opposite of that. All right? Makes sense. Once you break it down into those three laws, it really makes sense. Okay? All right. Make sure you got your notes down there. For the next part, you're going to be using this chart. We're going to talk briefly about gravity, and then you're going to have a little exercise where you're going to utilize this chart. All right? Clearly, you can see Jupiter has the greatest gravity force, and of course, that's because Jupiter has the greatest mass, right? The more mass you have, the more pull of gravity you will have. All right? When you go to the moon, of course, is much, much smaller than the Earth, so it would have a much lower pull of gravity. In fact, it's 6 times smaller than the Earth, so it has about 1/6 the gravity as the Earth does. Okay? So here's where we tie in Newton with this whole gravity thing. All right? Gravity is controlled by 2 things, mass and distance. All right? A large mass, if you put them close together, you're going to have a high amount of gravity. A smaller mass, move them farther apart, well, you're going to have a lower gravitational attraction. Okay? These 2 graphs, hit pause, take a second, see if you can figure them out. All right, over here, if distance increases, what will happen to gravity? As I get further apart, there should be less gravity. So yes, the further apart you go, the gravitational attraction will decrease. Notice that's an exponential decrease. And vice versa, if you get closer, right, if there's less distance between them, then the gravity will increase exponentially, right? You'll accelerate faster and faster and faster as you get closer to something in space. Over here, mass versus gravitational attraction, think it through. The more mass I have, the more gravity I have. So that's going to be a direct relationship. It is directly proportional. If you double the mass, you double the gravity. If you cut the mass in half, you cut the gravitational force in half. All right? And of course, this works very nicely with Kepler's laws to figure out the orbits of the planets. Okay? What would happen if the mass of a planet was tripled? 3 times the mass equals 3 times the gravity. There you go. Okay. So, here's what I was saying. You guys, using that other slide we had prior, you have to try to fill in this chart based on this data and, of course, right here. Now, these are pretty close relative to size, and that should help you answer some of these questions as well. And then, of course, there's some Regents questions to polish it up in the end. All right? Work hard on that, and we'll see how you did back in the meet.